Alright, so we're working on our second part of our review here. We begin with the dimensional analysis. So I'm going to go through the setup and show you how to solve for it. The single unit one is really easy. We just have 100 kilograms over 1. If you can make the trip to milligrams, that's fine, but most of us go baby steps to eliminate having to think too hard. So we say 1 in 1,000, and here we say 1 in 1,000. And we just end up moving it over 6 more zeros. So you can see it gets quite a bit bigger. So we can just plug this in our calculator if we want. We can just say 100 times 1,000 times 1,000, and we get this large number of adding zeros in here. And then you can check your units. That's what we wanted to get, was milligrams. That was our path. Milligrams, milligrams. We have unit agreement. That means we did it right. Okay, so we have the next one, which is a derived unit. You have 25 kilometers per 1 hour. We're going to go from kilometers to meters, hours to seconds, seconds to microseconds. So that's our path. Now we just got to fill in our equivalency. Who's bigger? 1 in 1,000. Who's bigger? 1. Now this is where a lot of you made a mistake, so don't make the mistake here. It's not 60. It's 3,600. Here we have 1 and 1 e to the 6th. So we're going to plug this in our calculator. 25 times 1,000 divided by 3,600. Whoops. Divided by a million. And you see we get this number right here. 6.9 e to the negative 6. And then we have our unit of meter per microsecond. So that's how we do that one. Next, here for the next one, we got 50 kilograms per milliliter. So we're going to go from kilograms to grams, and then grams to milligrams. Over here we want to go milliliter to centimeter cubed, and we want to go from centimeter cubed to meter cubed. So that's our setup. It's 1 in 1,000 for the kilogram-gram equivalency, 1 in 1,000 for the gram to milligram, 1 to 1 here, 1 and 1 e to the 6th here. So when we're all said and done, we just have to multiply. So 50 times 1,000 times 1,000 times a million. And we end up with 5 e to the 13, which is a big number, right? Scientific notation, 5, 10, 10 to the 13. And then we have milligrams per meter cubed. Now watch out here, right? This is where a lot of you make your mistake. It's not 100, it's 100 times 100 times 100, because milliliter is volume, right? This is a density, a derived unit, which has volume in it. And to get to meters cubed, you have to change your equivalency to make it so it matches that cubed relationship. So then we get down here to sig figs. With the sig figs, we have, I'm just going to underline rather than circle. In this one, we have 2. These are placeholders. They're not on the right side of the whole number if you're applying the right rule. Here, they're all significant. These zeros here are trapped, and this 0 is on the right side of the decimal, on the right side of a whole number. Here we have 4. These are trapped. This is not significant as it's a placeholder. It's not on the right side of the decimal. This tool is only good to the tens place. Here we have them all significant. They're on the right side of a whole number, and they're on the right side of the decimal, making them significant. This tool is good to the hundredths place. These are all significant, even though normally this is a placeholder. By putting that decimal point in there, we know that this tool is good to the ones place. That's the only time that the right rule doesn't apply. Prefixes. For prefixes, we have e negative 3. That's spelled wrong. It should be 2 L's in milli there. Centi, e negative 2. Kilo, e to the 3. Mega, e to the 6. Nano, e negative 9. And micro, e to the 6. Remember, micro has that goofy symbol of mu. I just want to remind you of that. When it's time to graph, you can set up your y and your x, meters and seconds, plot your points, establish scales, max scale of 125. Maybe do it by 25s would be a good way to do this. This has 5, so every 1. And you go through and you plot your points, and you get something that looks kind of similar to what I just drew here with points, and you get this quad relationship. So we plot our points in the graph, what relationship, quadratic or parabolic, the units of the slope. So if I pick any point on that curve and I draw a tangent line and I find its slope, I would see that the units for the slope would be rise over run meters per second, and that quantity would be velocity or speed. If I want to actually know the line's equation, there are a number of ways I can do it. One easy way to do it is see that this is going right through the origin, right? And that tells me that there is no b or c term. So therefore y equals something times x squared. So I can pick, this trial right here, and I can make this 5 something times 1 squared is 5, so you can see right away that it has to be 5. So y equals 5x squared. If I want to double check that, I can use my psi tools. I can go through here, open up psi tools, and take it to the data graph wizard. And once I get in the data graph wizard, I can add all these things, which I already did. It's always a good idea to remind yourself who's L1 and L2. So I had distance as L1 and time as L2. And I quit that menu and I want to go to the graphing window here. I want to hit scatter. And then I'm going to tell it that L2 was x, x is time, and y is distance. And you can see the same thing I just drew right there. If I quit this and I do a quad reg number 5, it will give me a best fit line that matches perfectly, or almost perfectly. And then if I hit y equals, it will tell me that relationship. Now this is kind of ridiculous. Look how far I get. 2, right? Basically 5x squared. Nothing for these guys, as we already knew it went through the origin. So it just proves that 5x squared business that we just talked about. Alright, so that's your review. Hopefully this helps, and study